Right, question 7. So you had to, for the first question, identify the type of reaction that's in step 1. So we're starting with ethene. We're adding hydrogen to it to give ethane. There's a number of possible answers there that you could have given. It's simply an addition reaction, which is what you were taught at GCSE, and we haven't done much organic chemistry yet, so I'll forgive if you haven't got that, but really you could have said it was the reduction reaction, which also gets the marks that either of those would do. There's all sorts of funky answers, like that some people gave hydrogenization or something like that, but hydrogenation was also an unheld answer. All of those really you should have been able to do from what you've been taught so far. So I don't know, not recently studied, so I'll forgive you for that reason. The enthalpy change for step 2, it says use 13 of the data book. This is enthalpy changes of formation data. So anyone who used enthalpy change of combustion data was not given the mark, especially those people who told me that surely the question was wrong. But no, you have to use enthalpy change of formation data for this. And you know the enthalpy change for a reaction is equal to the sum of the enthalpy changes of formation of the products, take away the sum of the enthalpy changes of formation of the reactants. In other words, the enthalpy changes of formation of those which you can look up, the enthalpy changes of formation of that thing which you can look up. This will be 0 because it's an element and they all have enthalpy change of 0. So you just plug the numbers in you've got in your data books. The enthalpy change of formation of carbon dioxide was minus 394. That's one of the products, so 2 lots of minus 394. Add, because also it's a product, 3 lots for water. Water was minus 286. 3 lots of minus 286 for water. And then we taking away the enthalpy changes of formation of the reactants, and there's only one reactant that's got an enthalpy change of formation, which is the ethene. Look that up and it comes to, I think it was plus 52, so we just write 52 there, and that came to, I believe, minus 1698. When you look at the mark scheme, it will say minus 1697 because one of the values is different in your data book from the one that this paper came from, so it's out by 1. For part C, you do exactly the same thing for step 1. That's the best way to do it, the easiest way to do it, the enthalpy formation of the products. That, take away the reactant, that gives you minus 136. So that's the way I'd have recommended to do it. It's the easiest way of doing it. So just for your benefit, look it up. It is minus 84, take away where is it, 52 again, same as before, comes to minus 136. Or if you wanted to, you could have worked out or looked up the enthalpy change of combustion of ethane, which is in the data book, and that is, well, at least in the old data book was 1561, and you could have done it from the enthalpy change for the reaction here is equal to that value, take away that value, using the whole clockwise anti-clockwise thing, so with this arrow against that arrow, so that value minus 1698, take away minus 136 would have got you the answer as well. There's another way you can do it, I'm sure, as well, using combustion data, but you should have got 136 using the method that I showed you. And then question 7D was tough. I thought that's not it. There's question 7D. Pause. By the way, I'm not making videos on the other questions right now because I'm hungry, and so I'm going to do question 7D and then the last question, and then I'll stop. So suggest one reason why the calculated value of delta H cannot be or can be considered either accurate or approximate. There's a whole array of possible answers here. So what I'm going to do is I'm going to point the camera at my screen, which has got the mark scheme there, and there's all of the possible answers, loads of possible answers. There's allow you to read those. We've got no approximations made in the cycle, values are specific to the compounds. Some of you just talked about it's Hess's law or what Hess's law was. I didn't quite think it was enough to say that. Small uncertainties associated with those. I thought this was really difficult to get the to get that first mark. Okay, there's something about the values being specific to the compounds, or have small uncertainties. I quite like those. The reason you could say it's approximate is because the values that we've got have been determined experimentally, which means they had uncertainties associated with them. And so some of you got that, or hinted at that at least. And also the values are only given to 3 or 4 sig figs, so there is an uncertainty associated with that. You can, or there is a lack of precision at least associated with that. So that's one reason that they're approximated. And there's a few other possible answers there which you can read. Okay. As I say, I thought question 7D was really tough, but it's only worth a couple of marks, so not the end of the world. Right, so here we go. High level kinetics was a bit of a battle for some of you. So you've been given a reaction mechanism, and normally they would give you a reaction mechanism, certainly for your course, and you might have to interpret it and discuss it. But you were told, you were asked to classify B and D as either reactant, product, catalyst or intermediate based on the mechanism. Right, so A and B are clearly reactants because they're the first things in the pot, and they're not regenerated at all anyway, they're not reformed. So A and B are both reactants, and the question's about B, so I've written down reactants there. And B is formed in the first step, and in the second step it is used up, which means it is not a product of the overall reaction, nor is it a reactant of the overall reaction. It's used up, so it must be what we call an intermediate. So that was done reasonably well. And the rate expression, now the rate expression is involves the substances which are involved in the slow step or before the slow step of a reaction rate at appropriate power, depending on how many there are in the slow step or before the slow step. In the slow step, which is the first step, which makes it nice and easy. And by the way, a rate expression you must say rate is equal to, and then give a rate constant, and then the concentrations raised to the power of how many there are in that slow step. For each of those, it's 1. There's 1 of them. So that is how you would do that rate expression. The last one, you have to work out the initial rate. You could fill it in that box or put it in the box underneath. But the concentration of B doesn't change, so the rate is not going to go up, clearly, because that's not changing. But the rate does go up because the concentration of A increases. It goes up by 1.5 times. Because it goes up by times by 1.5, it goes up by 1.5 times. And so the rate must go up by 1.5 times because it's first order with respect to A. And so 1.2 times 1.5 is equal to 1.80. And you should have given the units there. Given they were given in the question, you didn't need to. Alright, so that's how you do question 10. And that's it. Hopefully you enjoyed that. Hopefully it was useful. Do feel free to ask questions.